In this video, we'll begin by looking at binary numbers and understanding what binary numbers actually are and represent. We'll then focus on converting binary numbers into our number system of decimal, and then we'll focus on converting our numbers in decimal back into binary. So whether you realize it or not, there are actually a variety of numbering systems in our world today. The one that you are most familiar with, whether you know what it's called or not, is the decimal number system. So this is the number system that we use in our everyday lives, and this is what is called a base 10 numbering system. And that's because each of the spots for numbers is represented by a 1 spot, a 10 spot, a 100 spot, a 1,000 spot, so on and so forth, and they're all based off of being a power of 10. Now, the binary number system corresponds with the machine language that a computer can read. And the binary number system consists of just ones and zeros, and it is what is known as base 2. Then we have the octal number system, which oct hopefully sounds like octagon to you, and this is a base 8 number system. And then finally we have the hexadecimal number system that is base 16. So these are the four numbering systems that we are going to focus on. We're going to start by diving into binary, and then we'll eventually move forward into octal and hex. So before we dissect the binary number system, I really want to look at our current number systems. Remember, decimal is our current number system, and it is in base 10. So what I mean by that is that every single space here represents some power of 10. So the one spot, whether or not you realize it, is 10 to the power of 0, because 10 to the power of 0 is equal to 1. And what this one spot tells you is how many ones you have. You then have, the 10 to the first, which is 10. So this tells you that you have 9 tens. This tells you that you have 3 ones. And then we go to the 10 to the second power, which is the hundreds, and this is saying we have 0 100s. And then 10 to the third power is the thousands. This is saying we have 7 thousands. And then we have 10 to the fourth, which is, here we have 1 10,000, and then we can go so on and so forth with more powers of 10. So this is how our number system is created. And the other detail I want you to notice here is that all of the digits that make up a number in the decimal number system are digits from 0 to 9. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And if you count, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possibilities. So you can see that it is base 10 because each little spot represents how many powers of 10 we have in that particular spot. And then there are 10 possibilities for the digits here. So keep this in mind as we look at binary, because binary is going to be very similar. It's just binary is going to be base 2 instead of base 10. So binary, as we've stated a couple times, is base 2. But it's the same idea as the decimal number system. It's just based on powers of 2 instead of powers of 10. So the first thing you need to realize is that because it is base 2, we can only have 2 digits. So that means we only use zeros and ones. Because it is base 2, each one of these digits can only be one of 2 numbers, 0 or 1. The other thing you need to realize is that we use the powers of 2 here instead. So each of these slots represents something different than what we're used to. So where in base 10 it's telling us how many ones, tens, hundreds, thousands, and 10,000s we have, now we're using the power of 2. So 2 to the power of 0 is still equal to 1. So this first spot is telling us we have 1, 1. Then 2 to the power of 1 is 2. So this spot is telling us we have 1, 2. Then 2 to the power of 2 is 4. So this is telling us we have 0 4s. And then 2 to the power of 3 is 8. So this is saying we have 0 8s. And 2 to the power of 4 is 16. So this is saying we have 1 16. So keep in mind this is a different base So each digit here represents something a little bit different. These represent powers of 2. So as we try to convert between binary and decimal, we have to keep the different bases in mind. So in order to convert a binary number into decimal, what we essentially need to do is we need to figure out what each of these different numbers represents. So we can see we have the binary number of 11001101, which to us doesn't mean a whole lot. But if we remember our powers of 2, remember 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, so on and so forth, we can essentially see what is making up this number. So here we know that we are using 1, 1. So this particular digit here is representing 1. We then can see that we aren't using anything in the 2 slot. There's no 2's, but we have a 4. We have 1 8. We don't have any 16's. We don't have any 32's. We have a 64, and we have a 128. So what we can do is we can take these numbers. So we have 1, 128, 1, 64, 1, 8, 1, 4, and 1, 1. And we can essentially add together the powers of 2 that were used to create that binary number. So if we add together 128 plus, this should be 64, plus 8 plus 4 plus 1, we end up with the total number of 205. So that number of 11001101, if we break down the powers of 2 that make up that particular binary number and we add them together, we end up with a decimal number of 205. So believe it or not, these two representations here represent the same number, just in different number systems. So let's try another example on our own. So we're going to convert this binary number into decimal, and we can see that this current number is binary because of this base 2. So that's telling us this is a binary number that is written in base 2. And essentially what we're going to do here is we're going to go through and see which powers of 2 we need in order to create this binary number. So here I can see that this is my 1 spot because that's my 2 to the power of 0. And I don't need that slot, so I don't need that one because there are no 1's in this particular problem. This is my 2 to the power of 1 spot, so this is 2. And I do in fact need this one, so I do need the 2. This next one would be 2 to the power of 2, which would be 4, but I don't need it because there's a 0 there. Then move on to here, I have 2 to the power of 3, which is 8. And I do need that one because there's a 1 there, so I have 8. Here I have 2 to the power of 4, which is 16, and because there is a 1 there, I need 116. I then need 2 to the power of 5, which is 32, because there is a 1 there, so I need to have at least 132 in my problem. Then this is 2 to the power of 6, which is 64, but I don't need that one because of the 0. And then here I have 2 to the power of 7, which is 128, and because there is a 1 there, I do in fact need that one. So here I can see that this binary number is made up of 128 plus 32 plus 16 plus 8 plus 2. And if I take a calculator and add those together, I find that I have a total of 186. Now, because I want to make sure that I denote numbers differently, this is 186 in decimal, which is base 10. So what I have found here is that the number 10111010 in binary, if we convert it into decimal or base 10, is 186. So what I'd like you to do on this slide is take a minute, pause the video, and practice converting the following binary numbers into decimal. So use your knowledge of base 2 to convert these into their decimal base 10 equivalent, and then from there you can unpause the video and go check your answers and see how you did. So please check your answers here, see how you did. If you have any questions, please let me know. If you want to be super technical about how you write your numbers, you would write all of these with their little base 10 to indicate that these are numbers written in decimal, where the other numbers were written in binary. But again, check your answers, see how you did. If you need any support, please seek support before moving on. So what we're going to do here is we're going to take this process and reverse it. So now we're going to take a decimal number. So here we can see this is base 10. And we're going to convert this decimal number of 93 into binary. So we're going to have to remember that binary is base 2. And what I like to do is I like to find all of the binary numbers in order of base 2 all the way up to the first one right past 93, because we don't need anything like super large. If we get up to 93, we can stop. So we know that 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 squared is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32, 2 to the sixth is 64, 2 to the seventh is 128, and because 128 is larger than 93, I can stop there. I don't need to go any higher. Now, what I'm going to do here is I'm going to determine which values are needed to make up 93 using binary. So I'm going to go through the numbers one at a time, starting with the largest, and I'm going to start to build my number 93 into binary. So what I do is I start with the largest binary number that is smaller than 93, which in this case is 64. So what that tells me is I'm going to need 64 in my binary number in order to build the decimal number of 93. So what I do is I take 93 and I subtract 64. So 93 minus 64 becomes 29. So I can see that I definitely need 64, so I'm going to need a 1 in the 64 spot, and I'm left with 29. Now what I notice here is that the 32 is bigger than 29. So what that's telling me is that I will not need 32 to build my binary number, because 64 took care of enough that 32 isn't needed. So I'm going to put a 0 there. I then look and see that 16 is less than 29. So I'm going to subtract 16 from 29, and that leaves me with 13. So I do need 16. I then also need 8 because that is smaller than 13. So I subtract 8 here. That leaves me with 5. I can also see that I need 4. And that leaves me with 1. Because 1 is smaller than 2, I will not need the 2, so that one becomes a 0. And then I do need the 1, which then becomes 0 at the end. So, as I construct this, what I find is that this number right here is actually my binary number. It represents that I need 64, 16, 8, 4, and 1. So what we're going to do is we're just going to write this, but we're going to write it horizontally. So I had 64, then I had no 32, I had a 16, an 8, a 4, I did not have a 2, and I had a 1. And then that is base 2. So all we're doing as we build those decimal numbers is we are looking for which powers of 2 we need to add together in order to create that number of 93. So here, if you were to, reverse the process and convert that binary number back into decimal using your knowledge of powers of 2, you should go right back to 93. So what I'd like you to do here is I'd like you to take a minute, pause the video, and practice this concept. See if you can take the following decimal numbers, these are all base 10, and convert them into binary numbers. So use what we applied on the last slide to practice converting these numbers into binary. And then once you are done, you can unpause the video and you can check to see if your answers are correct. So go ahead and check your answers here. Remember that all of these answers here are in binary, so it's a really good practice to write them all as base 2. As you're checking your answers, please double check that it matches exactly the order of the numbers from left to right, where there are 1s and 0s. If you're having any issues, please seek support before moving on. However, if you got them all correct and you feel like you've mastered this topic, you are able to move on.